Okay, so hi everyone, welcome to the week 6 of the lecture series on thermal physics on NPTEL. This is the tutorial session related to the week 6 lecture content, right? So, mostly, like always we have 10 problems which are mostly related or sometimes even exactly similar to the problems that you are given in your actual assignment. Okay, and we'll be solving that together here, and so that you can have the idea and you can solve rest of the problems. If there's something new, you can solve them by yourself, or even if you have some other questions related to such kind of concepts, then like problem solving aspect I am talking about, so then that you can also ask me in these live tutorial sessions, right? So let us start then with this week's problems. So as far as I can see that this week's lecture is mostly, at least from the problem context, this is mostly based on the behavior of real gases, like van der Waals equation of state for real gases, and the critical coefficients. Some parts of that was also introduced in the last lecture, and therefore there is a problem related to critical coefficient, which I remember that I solved that thoroughly for you, how to determine the critical constants like critical temperature, critical pressure and critical volume for when you are given a particular equation of state. And in that week 5 we solved that for van der Waals gas equation of state, and we calculated from our calculation we got Tc, Pc and Vc, which are the critical values of temperature, pressure and volume, right? And so this week's lecture and the problem series also contain some parts of the van der Waals equation of real gas, then the other equations of gases that are there to explain the behavior of real gases, then the idea of virial coefficient, which is something new that was not described in the earlier week. Then after finishing this behavior of real gases, we have something about the temperature concept of the thermometric properties, like how do you measure temperature, like resistance's dependence on temperature, or rather how do a gaseous system can actually have a constant volume, and from the change of its pressure as a quantity, as a thermometric quantity, we can back calculate the temperature that it is in, right? So these are the main concepts that we'll be covering, that the problems are based on in this week's assignment. So yeah, let us begin. So problem number 1, let us read that first. That calculate the van der Waals constants for hydrogen given that Tc equal to 33.2 Kelvin, Pc equal to 12.8 atmosphere and R equal to 0.082 liter atmosphere per mole Kelvin. First of all, you notice that this Tc, Pc are the critical temperature and critical pressure for that gas, and it is mentioned that van der Waals constants you have to calculate. So this is considered as a van der Waals gas, obviously, and the gas is hydrogen. So you have to calculate the van der Waals constant. That mean they need you to calculate the value of A and B, right? Because van der Waals equation has these two constant values, which are basically corrections over the ideal gas equation that van der Waals introduced in his equation, where the constant A comes from the correction about that the gas molecules are not inert, they do interact with each other, which was not considered in ideal gas assumption. And the new constant B arrives because now in van der Waals equation of real gas behavior, we considered that the gas molecules, even though very small volume, but they do have a finite size volume which is non-zero. And in the ideal gas assumption, we just assume that the ideal gas molecules are like points which do not have any volume. So based on that, it was oversimplified, but in van der Waals equation of state, these are the two major modifications that actually changed the scenario from ideal gas to real gas. Basically, by using the van der Waals gas equation, most of the experimentally observed behavior of gases in reality could be explained much better compared to the how it was being explained by the ideal gas situation, right? So these two are the van der Waals constant. By van der Waals constant, you always have to remember, you are mentioning about A and B, right? So because you know the van der Waals equation of state for gases, right? So, and you know the expressions of Tc and Pc. So basic idea is that you have to use both those informations, like the expressions about Tc and Pc. From there you have to have an idea, and then from there you will get the values of A and B. Also remember that units, you have to take care of the units, whether they are all in the same unit or not. So in this case it is temperature in Kelvin as always, but P, the pressure, is in atmosphere unit, and R, therefore the universal gas constant, is also given in liter atmosphere per mole Kelvin unit. So you do not need to convert anything into some other unit, because all of them are in equivalent units, right? And hence A and B will also have units related to these units, like pressure will be in atmosphere, volume will be in liter, and temperature as usual Kelvin. So TC is 33.2, remember, and PC is 12.8. So let us choose a blank page and start calculating. So question number 1 is that for van der Waals gas, which is hydrogen in this case, the TC and PC value is given. So first of all, the van der Waals equation of state, if you remember, I will write it down once again. P plus A by V squared into V minus B equal to RT. This is for 1 mole of gas. So 1 mole of van der Waals gas has this equation. This is considered per mole. So N is taken as 1. If you have gas number of moles which is not equal to 1 but more than 1, then you also have to include a N factor in this equation, which comes here P plus N squared A by V squared, then V minus NB equal to nRT. Basically you then substitute your V by N factor. Then you get the ideal van der Waals gas equation for N moles of gas. But here for now we are only considering per mole. So basically 1 mole has this equation. And here as I told you that I solved this for you in the week 5 tutorial. You can go and check if you have not seen that we have calculated thoroughly the mathematical calculation of how critical values of temperature, pressure and volume are calculated or obtained starting from the van der Waals equation, which is this equation. So I'll not repeat that again in this tutorial, but rather I'll directly use those known values, assuming that we all know that okay, these values should come because we have derived those values earlier, right? So for van der Waals equation, because these critical values are dependent on the equation that you are using. If you are not using van der Waals equation, if you are using a different equation, then obviously the values will be different. So for this particular van der Waals equation, we have the values as PC equal to A by 27B squared and TC equal to 8A by 27RB, right? So and also the critical volume has an expression like Vc equal to 3 times B, but in this question there is no mention about volume, so we'll be needing these two expressions only. And here A and B are the constants which are known as van der Waals constants, okay, where A comes because of the correction in molecules interacting with each other. And the term B, which comes because of the correction that the molecules have a finite volume. They are not point-like. And these are the corrections made to the ideal gas equation. So however, we move on to our problem here, that PC and TC value are known. Now you have to know what is A and what is B. First of all, you can take a direct ratio of PC by TC, right? So let us take a ratio so that some of the parameters are already cancelled out. So A by 27B squared by TC means into 27RB by 8A. So this A and A cancels out, and this 27 cancelled out. So this R divided by this B square and B makes it only B. So R by 8B. PC by TC equal to R by 8B. Now you have to, you see that here instead of both the two unknown parameters together, now we have reduced the expression in such a way that you already know the right hand parts. One second. Yeah, okay. So you basically already know the left hand side's value, right? PC by TC. So you just use that value because from the equation they have provided you that value, and you know the R, that is a universal gas constant. So from here your problem has been simplified, that you have only one unknown constant on the other side, and you can directly calculate its value by using all the other known values. So uh, B is here equal to R by 8 into TC by PC, because B comes here, then R by 8 into TC by PC. So this is 0.082 liter into atmosphere per mole into Kelvin divided by 8 into what was TC? TC was, I think, temperature, so it is 33.2 Kelvin divided by PC was 12.8 atmosphere. So first of all, this atmosphere cancels out. This 1 by Kelvin into Kelvin also cancelled out. So calculate, what you are left with is 0.082 into 33.2 divided by 8 into 12.8. So this is like you are getting 0.0266, and remember the unit. So here per mole is left, and yeah, liter is also left. So liter per mole will be the unit of B, which is also obvious from the dimensionality. If you check that B is with V, so B will have a unit that will be related to V obviously, but you here have V minus B equal to RT for 1 mole. So obviously you have to add that per mole in the units as well. So therefore you have volumes unit, which is liter divided by per mole. So this is your B value. And then what is your A value? This is the other unknown parameter that you can now easily calculate, because you know already the other parameter B. So like for say from PC only, you can put the value of B here and you can directly get A. So here A is equal to 27 into PC into B squared. So A equal to 27 B squared into PC is equal to 27 into 0.0266 whole squared into PC is here, you know that 12.8 atmosphere. So also you have to here take care of the fact, because this is liters this is liter squared by mole squared, right? And then PC is equal to so I have to also, not here, I have to also write down the unit so that you don't confuse what unit we are using. So this atmosphere comes from the pressure unit, but this B square that I have written here, I have not put down the unit here, so I will write down the unit on the right. So this is liter square per mole square, right? Because this is B squared, so this will be this unit whole square. Now calculate the value that you have 27 into 0.0266 whole squared into 12.8, which is like 0.24. So let us go back whether they have, yeah, so if you look at this, you will see that even if our pressure in the question was given in atmosphere units or everywhere, but in the answer options they have given us a value where the pressure is coming in bar units. So you have to change or convert from atmosphere to bar to actually get to answers that are matching with those options. Otherwise you would get a exact answer which is also correct, but that will be in your atmosphere will be the pressure part of that equation of the unit, but here you need to match with the given options. So then you will have to convert that into the pressure units of bar, right? So you know that this is a standard conversion, that 1 atmosphere equal to 1.013 bar. So by using this, whatever is here, so we have got from the rest of this is 0.244 what was that, atmosphere liter square per mole square. But now we want to convert into bar, so 0.244 into 1.013 liter square bar by mole squared. So into 1.013 means this is 0.247. Whether you are getting it or not, let us check whether we have done the calculation right. Yeah, 0.247 is their option. So 0.247 bar liter square per mole square, just like we had, and the second option is also matching. So the correct answer is A, which is what we have obtained. So let us put down the unit also. So here to 0.247 liter square by mole squared into bar. So this is the value of A and this is the value of B. These are the two results that we have obtained from the question number 1. So question number 1 is solved. Then move on to question number 2. It is saying that calculate the Boyle's temperature of 1 mole of a helium gas using the van der Waals constants, which are A and B, that is given. Okay, and R value is given, which is the universal gas constant, and the number of moles is given as 1, and you have to calculate the Boyle's temperature, which is often written as T subscript B. Okay, so first of all, to solve this, because you have the information about A, B and R and also the number of moles, and from there you have to get what is TB. So there has to be a relation. So I can directly use that formula either, but I would also like to go into a bit detail that how that formula is actually coming of Boyle's temperature. So okay, so let us solve question number, let us solve question number 2, derivation of Boyle's temperature. Okay, so Boyle's temperature first came into the picture when the ideal gas equation was not really matching the experimental results that we see from real gases. So to actually counter that, to actually come up with a better equation that fits the experimental results, some of the scientists suggested some other equations as well. So at that point of time, Camerlingh-Onnes was the person who suggested one equation which is not a theoretical equation. It was just an empirical equation based on the behavior of the experimental results that is seen from those real gases. So he suggested an empirical equation to explain the behavior of gases in reality and not like the ideal gases assumed behavior, often suggested an empirical equation which is also sometimes known as a virial expansion. Okay, so this is basically written like PV equal to A plus BP plus CP squared plus DP cube plus dot. So you can see that the P times V, which is for the ideal gas written as simply as RT for 1 mole, but here on the right hand side you have terms which are dependent on pressure with higher orders of pressure as you go from P to P squared, P cube, etc. And each of them has a coefficient with them like A, B, C, D. So this A, B, C, D are called virial coefficients, which has this A is called first virial coefficient, B is the second virial coefficient, C is third, D fourth, and similarly like that is continuous. So these constants are not really constant because they depend on temperature and they also depend on the type of gas that you are dealing with. So these are very specific to what kind of gas that you are using and also on the dependent on the temperature. So this is basically saying that even if ideal gas suggests us that this right hand side is just a constant at a constant temperature because it is RT, but from Camerlingh-Onnes expression to actually fit to the behavior of real gases, it was said that no, this right hand side is not entirely constant, but it has some pressure dependence which is gradually decreasing with higher orders of higher order terms. Like if you go from A to B, so B will obviously be of a lower weightage than A, but it is dependent on linear in P. Then if you go from the second to third term, that is P squared, it has a coefficient of C, whose value will be much smaller than this A and B's value, and similarly that value of D will be even smaller, and gradually as you go towards the higher order terms, the contribution of those terms will be even decreasing compared to the earlier terms. So this is a gradually decreasing strength of higher order terms, but these are kind of a, you can think of it like a correction to the already existing van der Waals expression, ideal gas expression, and to fit to the real gas behavior, it is just an empirical formula, just adding different correction terms with proper coefficients to the equation. These A, B, C, D, etc. are those coefficients which are there in the correction terms, and these are called virial coefficients. Okay, where A is the first virial coefficient, B is the second virial coefficient, C is third, and similarly it continues. So just a second. Alright, so so you're discussing the virial coefficient and virial equation, virial theorem basically. So here for explaining the real gas behavior, so basically this was an empirical equation given by Kamerlingh once. So instead of a constant term on the right hand side, he actually introduced some higher order terms depending on different orders in powers of pressure, and the coefficient that are included with that is called different orders of virial coefficient, first, second, third, etc. So as you can see from here that so as I said that the higher order terms, HOT is the short form of higher order terms, are of decreasing values. That means as you go from A to B to C to D, gradually their values will decrease. So basically their contributions to PV on the left will also decrease. Only when the pressure is very high, then only this P cube or P to the power 4 etc. terms will contribute, right? Otherwise you will not have to use those terms again. So normally for real gases, if the pressure is moderate pressure or low pressure, so low or moderate pressure, so this is not too low as in P tends to 0 low, so this is just normal low or moderate pressure. Then these higher order pressure terms will be neglected. Higher order terms in P squared, P cube, etc. are neglected, so we are only left with PV is equal to A plus BP. So the first two terms, first constant term and the second term, that is linear in pressure, because the pressure is not too high, so we'll not need the higher order terms, because anyway the coefficient corresponding to the higher order terms are too small, so we can neglect that, right? So PV is equal to then A plus BP. This is not constant, we can see here there is a pressure dependence. Now we know for ideal gas, that is based on the ideal gas equation, we know that PV is equal to RT for 1 mole, right? So PV is equal to RT equal to constant when temperature is constant. That means here P into V is a constant on the right hand side, but for a real gas the behavior is different, it is not entirely constant, but there is a linear dependence on pressure. So this is caused by this coefficient, second virial coefficient called B. B is causing all this thing because A is just the first virial coefficient, but this is constant, so this can take this term. But the second one that is involving, that is actually giving contribution to the second term, which is actually linear in pressure, is because of the second virial coefficient B. Now this B has a specific behavior that is experimentally seen, that B is less than 0 at low temperatures, and eventually it is greater than 0 when temperature increases at high temperature. So with temperature there is an evolution in sign of B. So with temperature, as you go from low to high temperature, the sign of B, the coefficient B, changes from negative to positive value, right? So there has to be a point, there has to be a temperature where the sign change actually occurs. That means you, whenever you are going from negative to positive, there should be a zero crossing point as well. So that particular temperature where this zero crossing happens, that means where B value is just transitioning from negative to positive, or in other terms B value is just zero at that point, that is called the Boyle's temperature. So at the transition, or which is the zero crossing point, so this coefficient value B is then 0, and this point we we identify as T is equal to TB, which is the Boyle's temperature. Why this is Boyle's temperature? What is the significance? Because at T equal to TB, because here B equal to 0, then the gas expression can be written as PV is equal to A plus B into P, where B becomes 0, which is just A, that is equal to constant, or constant that is only temperature dependent. Okay, so now you can you can, so basically you can write it like, compared to, we can compare it with like PV is equal to RT is equal to constant when T is equal to constant for ideal gas. Okay, and this one is for real gas following this virial theorem, but only at T is equal to TB, this is valid, that PV is equal to A equal to constant. So at a particular temperature T equal to TB, real gas expression PV is equal to A equal to constant dependent on temperature tends to ideal gas equation, which is just PV is equal to RT is equal to constant at constant temperature. So because of this similarity, this particular temperature is significant and it is called Boyle's temperature. Okay, so how do you calculate then Boyle's temperature? Because PV is equal to, you have seen that it is A plus BP. So if you take a derivative of PV with respect to P, that means del P of PV is equal to just 0 plus B, right? So if at T equal to TB, the condition you need is that B equal to 0, that means you need del P of PV equal to 0 here, right? Yeah, del P of PV is equal to 0 at the Boyle's point, Boyle temperature point. So this is one of the way to get to know what is Boyle temperature and how to get that. But here for our case, because we need the formula for Boyle temperature in terms of the van der Waals constants, which is A and B, because in the question you remember that they have asked you, this question number 2, they have asked you to calculate the Boyle's temperature when you have the information about A and B, which are van der Waals constants. So typically we have to in particular use the van der Waals equation of state and get the value of TB. Now this is, the heading should be determine TB for van der Waals gas. Okay, so van der Waals gas, you know that expression, that P plus A by V squared into V minus B equal to RT. This is for 1 mole, right? So you can simplify these terms by reorganizing it, that P equal to then RT by V minus B minus A by V squared. Or if you want product of P and V, then PV is equal to RTV by V minus B minus A by V, right? Now yeah, so let us continue. RTV by V minus B, A minus V. Now we know that at T equal to TB, that means at Boyle's temperature the real gas behavior tends to ideal gas. So that means at T equal to TB, PV should be is equal to R TB. This is ideal gas behavior. PV is equal to RT, but this is only valid at a single point, which is the Boyle's temperature point. That is why we replace T by TB. Okay, so this is at T equal to TB. You know that PV will be equal to RTB by this significance of Boyle's temperature. But if you already know the PV value from that actual van der Waals expression, so these two have to be identical or equal at the point T equal to TB. So that is what we'll do, that we equate the both TB values we got from two different cases, and we'll equate them. PV at T equal to TB will be R TB. So here using this expression we replace the T by TB here. So RTB V by V minus B minus A by V is equal to RTB. Right, so we get RTB common, V by V minus B minus 1 is equal to A by V. So R TB, V minus V plus V B, then V minus B is equal to A by V. So you get TB is equal to A by V into V minus B by B into 1 by R. So this is like, so now you know that V, that is the total volume of the container, is much greater than the co-volume correction of B. So by that sense you can always neglect B with respect to V. That means V minus B can be almost approximated to be nearly equal to V. So that is what we do for simplification. A into V minus B approximated as V into 1 by R. So this V and V cancels out. So we get TB is nearly equal to A by. So this is the approximated formula for Boyle's temperature for van der Waals gas, because this is given in terms of the van der Waals constants A and B. Now once you know this, you can directly use this formula and solve this question number 2, that is basically, so now TB is equal to just A by RB. So A is equal to 3.59 into 10 to the power minus 3 divided by, take care of the units of course. So here force is given in Newton, pressure is given Newton and Newton per meter square unit. So pressure is force by area, and then Newton meter to the power 4 by mole to the power minus 2. Then B is also meter cube per mole, and R is joule per mole Kelvin. So basically this is A by R is 8.31 into B is 2.41 into 10 to the power minus 5. So what do you get? Just calculate. 3.59 into 10 to the power minus 3 divided by 8.31 into 2.41 into 10 to the power of minus 5. So this is 17.92 Kelvin. Okay, so 17.92 Kelvin, we mark this answer. This is option number B is our correct option in this case. Now question number 3. The second virial coefficient beta of a gas is 0.02 liter per mole. Then calculate the volume of 1 mole of the gas at 20 degrees centigrade, 27 degrees centigrade and 5 atmosphere pressure. Now there is a this thing that again there is a mention about the virial coefficient, second virial coefficient, and but this is beta, remember. So there are two type of expressions in which you can represent the virial theorem, which is an empirical theorem basically. One, in orders of pressure you add correction terms in orders of higher, different orders of pressure, and the other possibility is that you do the same thing but now in orders of volume. So there are two types, so either of them can be used. So based on this question, here the volume part will have to be used, whereas for question number 2 we had mentioned the pressure part. So basically virial expansion, so this is maybe called as virial expansion. So this can also be taken as PV, just like we took it like PV is equal to A plus BP plus CP squared, etc., where A, B, C, D are first, second, third, etc. virial coefficients. but this is in terms of pressure. Now, or it can also be written as PV is equal to, so before that this can be again taken like, because you know that this is the only constant term, all other terms are pressure dependent. So for ideal gas behavior, when P is tending to 0 at low pressure, real gas tends to ideal gas, right? So that means here PV tends to RT, which is the ideal gas equation. PV is equal to RT. That means if you put P equal to 0 all this equation here, we are only left with PV is equal to A, and for ideal gas PV equal to RT. So in other words, A equal to RT. So basically you can replace this by RT, and you can have a closed form of equation like RT into 1 plus BP plus CP squared plus dot dot dot. You can take it as B prime or C prime also, because now they are slightly modified from this B and C in terms of that now B prime into RT is equal to your total B, right? So this has to be multiplied. So this is within the product term. But this is one of the virial expansion type that you can use. Now the other type is expand in terms of V or volume. So then it will be like PV is equal to RT into 1 plus beta by V plus gamma by V squared plus all the higher order terms. So you can notice here that in the earlier expansion it was in terms of pressure, and pressure was in the denominator, right? But here pressure was in the numerator, but here the volume is in the denominator term, because pressure and volume are obviously inversely proportional to each other. So in this case it has to be in 1 by V order of expansion. So but the idea is the same, that the right hand side of that expansion is not just a constant like an ideal gas, but it has all the higher order terms present to explain the real gas behavior. So here your beta becomes the second virial coefficient, because first virial coefficient is always RT here in this case also. Now gamma in this type of expression is called as third virial coefficient, and all the higher order terms are present. Here in the same manner, as you go to the higher order, the contribution of the terms will gradually decrease. So unless you are considering those terms actually for high volume or for low volume, then you cannot consider the higher order terms. You always have to stop your equation at the linear expansion part, that means up to 1 by V part. But here beta is basically the after the first constant term, it is the most important or significant contribution to the PV part. So that is why in most of the questions you will encounter this beta, which is the second virial coefficient. Now you have beta here, right? So if small or moderate, then 1 by V is, so if V is not small, large or moderate, then 1 by V is basically small or moderate, because you know that for very large volume the real gas behavior tends to ideal gas, because then the volume is so huge that in with respect to the total volume of the gas, the molecule each volume of each of the gas molecules become negligible, and also they are farther apart from each other, so their interactive forces are also negligible. So it tends to behave like an ideal gas. So that is why if V is very large or moderate, or 1 by V is small or moderate, in those cases then you only stop your expression up to this point, and you do not consider all the higher order contributions, because they have very negligible contribution. So you just stop at PV is equal to RT plus beta by V. Okay, so then you simplify it further. PV is equal to RT V plus PV is equal to RT V plus beta by V. Here you get PV squared minus RTV minus RT beta is equal to 0. So here you get V equal to RT plus minus root over of R squared T squared. So basically you are solving for a like quadratic equation. How do you solve that? Basically the same thing, that minus B squared minus B plus minus root over B squared plus 4AC plus. So it is basically the kind of solution you get for x squared plus bx plus c type, where you have the roots like x equal to minus b plus minus, okay, root over of b squared minus 4ac by 2a. So similarly you can just compare this equation with this equation and you get this equal to 4ac means here 4p, this minus and minus makes it plus, so rt beta divided by 2p. So you get v is equal to rt plus minus, you take common another rt, so this is root or under root, so rt whole square you take common, and after it comes outside the root it becomes normal rt from rt squared. So this is 1 plus 4p beta by rt, okay, and divided by 2p. So you can even further simplify it and you get that v is equal to rt by 2p into 1 plus minus root over of 1 plus 4p beta by rt. So once you have that expression, let us go back that what are the information that is known to us, so we can calculate this thing. Like in the equation they have beta value 0.02 liter per mole in liter units, remember. Calculate the volume, so v you have to calculate, so v we have obtained from that equation. Number of moles is 1, so that is what we started with in Van der Waals equation for 1 mole. And the gas at 27 degrees centigrade, so T is given and P is given, beta is given, and you have to calculate V. So you have T equal to 27 degrees centigrade equal to 27 plus 273 equal to 300 Kelvin, and pressure is equal to 5 atmosphere, that is also given, and beta is equal to 0.02 what it was, liter per mole, I think, 0.02 liter per mole, right? So just make sure everything is in the same type of unit, so liter per mole. Now because all these are in liter, atmosphere, etc., so obviously R value will have to be chosen in this term, 0.082 liter atmosphere per mole Kelvin. So all the units are matched. Now V is equal to simply R is 0.082 into T is 300 divided by 2 into pressure is 5 into 1 plus minus root over of 1 plus 4 into 5 into 0.02 divided by 0.082 into 300. So if you calculate this whole part and only taking the physical answer out of this plus and minus both the answers, only get the physical answer, so which is physically valid. So this is positive value we have to obviously take because volume cannot be negative, right? So this is just 5.11 liter. So V is just 5.11 liter for this question concerning the second virial coefficient. So let us check here. 5.11 liter is the option number C, that is correct answer for this case. Now question number 4 is about a gaseous hydrocarbon obeys the DITEDC equation. I am not sure about the pronunciation whether I am making it correct or not, but this is another equation that I was talking about, that Van der Waals equation of state obviously gave us a new insight right from the ideal gas equation where it mostly could not match the experimental behavior of gases. Van der Waals equation was a huge improvement or a direction of for the research for explanation of the gas behavior in reality, but it has also some disadvantages, some mismatches with the actual observations. So to improve upon that, many other scientists later on came up with other equations as well. So one of such equation is this DITEDC equation, and there is a particular equation. I'll write that down what that equation is, but let us read the question before that. So it is mentioned that it has a critical temperature of 33 degrees centigrade, that means Tc is given, and critical volume also given. So Tc is given 33 degrees centigrade and critical volume Vc is given in liter per mole unit. So per mole you have to consider number of moles is 1 in this case, but later on it is said that calculate its pressure of 10 moles of gas occupying a volume of 4.86 liter at 27 degrees centigrade. So first they have mentioned to you the critical parameter TC and VC, and they have also mentioned that you have to use the diateries equation, and then you have to actually use the equation and calculate the pressure when you have all the other information about number of moles, volume and temperature. So basically there must have been some parameters, some unknown constants in that equation that you would not know unless you know the expressions of the critical parameters TC and VC. So let us jump to that. So the diateries equation, as I write, is basically, so this equation looks something like P is equal to RT by V minus B into e to the power of A by minus A by RTV. So this is for 1 mole. Okay, so for 1 mole of gas, this is the diateries equation. And if you have more than 1 mole, then you have to just replace that mole number as a factor on V. That means you have to replace V with V by N if there are N moles of the gas. So for N mole, replace V with the factor of N, V by N. So then pressure becomes P equal to RT by V by N minus B e to the power minus A by RT V by N. So this is simply nRT by V minus NB e to the power of minus A N by RTV. This is for N mole. And this is for 1 mole. Now, as you have already learned how to calculate the critical parameters TC and VC and PC when you have just the information about the equation of state for that particular case. I had already derived it with you in the earlier class for Van der Waals equation of state, but as an exercise you can also take it like an exercise to yourself, that let's say you have been given this equation, and using this equation you have to calculate the TC, VC and PC values. So the main technique that you need to use is just the same that you had used before, because at the critical point you know that the slope of the curve at equal to TC is equal to 0, and because it will be an inflection point where the curvature of the curve will change, so the curvature of the double derivative of dP by dV of the PV diagram will also be 0. So these are the two conditions to get the values of TC, PC and VC for any gas equation which has a connection between, shows a connection between PV and T. So here you can try for diateries equation, and you can if you solve this by yourself, so you'll see that you will get the critical parameter values as TC is equal to A by 4RB. So I am not solving it again by myself, you can try it out, or you can also see books or internet. This is standard, so I'll not get the same derivation again. So V is equal to 2B and PC is equal to A by 4E squared B squared. This is A. This is what we get from this type of a derivation, the TC, VC and PC values. Now in the question they have given you the value of TC and VC. VC value is not mentioned. So and also for this for this case we'll just take a product of VC and TC, and we'll see some of the terms will cancel out to simplify. So this is 2B into A by 4RB. So this B and B cancelling out, and this is just A by 2R, right? So then you have VC value given as 0.142, I think, liter per mole, and TC value is given in degree centigrade, so we convert into Kelvin. So 33 plus 273 Kelvin is equal to A by 2R. Now this is in liter and this is in Kelvin. So your A is basically one unknown constant for this case. So this is just 2 into R into this whole left hand side. Okay, LHS. So you put the value of R, because this is in liter atmosphere unit, so you need to use the value 0.082. Okay, and into this whole thing 0.142 into this thing. Okay, now let us calculate what this value of A comes as. So this is 2 into 0.082 into 0.142 into 306. So this is just 7. So we get A equal to 7.126, and we check out the like unit carefully. We have also seen the unit of A before, so it is like atmosphere into liter squared per mole square. So you can check the unit is right from the dimensionality of A again by yourself. You know how to do that, right? So then once A is obtained, so we can get the other unknown factor, which is B. So you know that this Vc equal to just 2b, right? So you can also directly use this Vc value and get B. So B equal to just Vc by 2, which is like 0.142 by 2, which is like 0.071 liter per mole. So you have both the value of B and A. Now you have to calculate the pressure from this diathesis equation when you have all the other information about the volume and temperature, and even the constants of A and B we just obtained from the critical constant value, critical parameter values. So now we just use the main expression that P is equal to nRT by P minus NB to the power of minus AN by RTV. So because here N is equal to 10 mole, that is mentioned in the question. For 10 mole you have to calculate, and V is given. So let us go back and see what is V and T values were given. Question number 4. So V value is given as 4.86 liter and T is 27 degree centigrade. 4.86 and 27. So V equal to 4.86 liter and T is equal to 27 plus 273 is equal to 300 Kelvin. So your pressure will be like P is equal to 10 into, because already this is in liter atmosphere also etc unit, so R is 0.082 into T is then 300 divided by V is 4.86 minus NV means this is N is equal to 10 into B is we obtained B, so 0.071. okay, and then e to the power of minus A is 7.126, so 7.126 into 10 divided by 0.082 into temperature is 300 into volume is 4.86. So if we calculate this, we will get a value of, I think, 32.66 atmosphere. This is your value of the pressure. So let us go back and check the answer option. Yeah, so option number D, that is the correct answer, and we have obtained that, right? So this is done. Then question number 5. Determine by using the reduced van der Waals equation how many times the gas temperature exceeds its critical value if the volume of the gas equals to half the critical volume and the pressure is 12 times the critical pressure. So this is very interesting because it is saying that the gas's actual volume V is half of its critical volume, that means Vc by 2, and the actual pressure P is 12 times the critical pressure Pc. So this is the two options conditions given, and now you have to use the reduced van der Waals equation. So this is I am sure that you have studied in the lecture content of this week that how to express the van der Waals equation of state. So in that part, then it is mentioning in the question that how many times the gas temperature exceeds its critical value. So just like you have V and Vc's relation, P and Pc's relation, similarly you need to have a comparison and relation between the temperature and the critical temperature. So T and Tc, how they are related. So T by Tc ratio you have to calculate. Let us call this T by Tc ratio as R. So TR you have to calculate. So basically we use the reduced van der Waals equation of state for this case. So like here we know that because actual van der Waal equation of state has the constants A and B, which are temperature dependent and depends on the type of gas that you are using. So to generalize this equation further, the constants A or B are removed from the equation, and after you remove that, that is called that is known as the van der Waals reduced equation of state. So basically the original equation is P plus A by V squared into V minus B equal to RT, right? So this is the original van der Waals equation. Now you know that if your critical values are PC, VC and TC, which value we do not know right now, so but you can always take a ratio of P by PC, the actual pressure by the critical pressure, and call it as PR. This is the reduced pressure. Then V by VC equal to VR, this is the reduced volume, and T by T is equal to TR because this is the reduced temperature. So here you can see that the pressure can be then written as PC times PR, V is equal to VC times VR, and T is equal to TC TR. So this we substitute in terms of this PC and PR, which is not directly pressure, but they are related to the expression of pressure. Okay, so this PR is basically dimensionless, right? So PC is only having the dimension of pressure. Similarly for VC and TC as well. So this PC into PR equal to P. Just substitute these P and V and T values in this equation. So you get PCPR plus A by VC squared VR squared. Right. Okay. So now, once you do that, you also know the critical parameter values of this van der Waals equation, right? So you know that your PC is equal to just A by 27B squared, B is equal to 3B, and TC equal to 8A by 27RB. So just substitute those known values into this expression, and what you get is that this PR into A by 27B squared plus A by VC squared is just 9B squared VR squared into VR into 3B minus B is equal to R TR to 8A by. So from here, if you take A by 27B squared common, so this is PR plus 1 by, so this is 27 is taken common and here it is 9, so it will be like 3 by VR squared into VR minus 1 by 3 because you have taken the 3B in common. So this 3B has come out, so this is VR minus this B is making it 1, and to adjust this 3, this is 1 by 3. So this is TR to 8A by 27B. So this is like PR plus A by VR squared to VR minus 1/3 equal to TR into 8A by 27B 1 by 3b. This is 8 dr by 3. So the Van der Waals reduced equation of state in terms of all the reduced parameter. So with all the reduced parameter and no dependence on specific gas dependent properties like A and B, you have um, okay, sorry, here I have this A left. This is not A, this should be 3, right? This is 3. So you have PR plus 3 by PR squared, PR minus 1/3, 8 by 3 TR. They just have to put the different expressions that they have given in the question. That, where is that here? So let me write it down first. That V is equal to half of VC. That means V by VC equal to PR. Half. So then P is equal to 12 times PC. That means P by PC equal to PR equal to 12. So you have the idea of the value of VR and you have the value of PR. So then it is easy to calculate the value of TR. So you have PR 12 plus 3 by VR squared means 1/4. So this you have, this if you solve, you will get TR is equal to 1.5. So this is your answer. This is the ratio of T by TC equal to 1.5, or T is equal to TC times 1.5. Okay, so from the critical temperature value, it is 1.5 times that. Let us take the option. So here if some of this has answered, our option is 1.5. So this is correct answer, 1.5. Now question number 6 is that at constant volume gas thermometer, the gas has to be filled at, what are the two conditions? Low temperature, low pressure, high temperature, low pressure, low temperature, high pressure, and high temperature, high pressure. So you know that for gas thermometers, where gas acting like the main substance and it is constant volume, that means if the to measure the temperature, it actually takes use of the pressure, right? So for constant volume, when the volume is constant, so the pressure will change and accordingly the temperature will change. So basically the constant volume gas thermometer, the gas is to be filled with what kind of gas? So because this um, actually works well for ideal gases. Okay, for ideal gases it helps or works well. So the gas has to be filled, it will be of ideal gas, but to maintain an ideal gas, what are the conditions that are needed? First of all, it need like low pressure and low pressure and high temperature. So that is the main criteria for the gas to behave like an ideal gas, because only then you can calibrate properly what is the thermometer's temperature scale corresponding to its resistance or etc. Okay, so High temperature, low pressure. This is option number B, that is correct. Okay, just the idea is that you know that for real gas tends to ideal gas when the either the there is a there are two main assumptions that actually contribute in this case. So real gas tends to ideal gas when based on those two assumptions, how much they are valid or not. Those two assumptions that ideal gas theory suggests or assumes that the gas molecules, each of them are of no finite size, their size is almost zero, like a point like particle. And the second one was that the gas molecules are interacting with each other and repelling or attracting each other, they are not inert. So but in reality this is not true, so therefore came the van der Waals equation of state, which actually deviates from ideal gas behavior. So there you have to but use almost closer to the ideal temperature range, ideal behavior. So in that case you are in that range of high temperature and low pressure, then it ensures that, because high temperature means the volume of the total gas in the container will expand. So compared to that volume, the volume of each small molecules in that gas will be very much negligible. So in that sense, high temperature actually guarantees that the gas molecules are occupying no space or because of their finite size effect, like it was assumed in kinetic theory for ideal gas. And the low pressure thing is because for low pressure the gas molecules are not tightly closer to each other, so they are much farther apart because of the low pressure. And same thing happens for low density as well, that if the density is low, then the molecules are not accumulated at one point, but they are spread out at different points. So at a single localized point, the interaction between the molecules will be very less. So basically for high temperature, because the gas expands, so its entire volume is much larger compared to the individual volumes of the gas molecules, so it actually deviates from the ideal gas law. But the it actually follows the ideal gas law, that okay. And the low pressure ensures that, the low pressure means you have the interaction of the gas molecules lower, so they are farther apart from each other. So in that sense, so low pressure and high temperature, and also low density, these are the things that are needed for a real gas to behave almost like an ideal gas, and therefore this constant volume gas thermometer was also because of that. So this is option number B. Okay, the more you increase the temperature, the more you expand, their intermolecular distance increases, so the internal interaction between the gas molecules are almost negligible, as if they are inert. And the volume occupied by each of the molecule is very small or negligible compared to the other molecules around, compared to the total volume of the gas. So these two assumptions of ideal gas are valid. And low pressure means the pressure that is pulling the molecules together is very low, so they are farther apart from each other, so again their force of interaction between the gas molecules is basically then lower. So when the interaction with the molecules is lower at all not considered, then it is almost like an ideal gas behavior. So this is the two conditions that are valid for our case. Okay. So we have covered till question number 6. Then question number 7 is about uh, the pressure of a gas in a constant volume gas thermometer is 80 centimeter and 109.3 centimeter of mercury at ice point and steam point respectively. So then when placed in a hot bath, the pressure reads 100 centimeter. Find the temperature of the bath. First of all, this question is related to the part that has been taught to you in the this week's lecture content in the very last, where the temperature and thermometric properties and how these properties depend and vary on temperature, and from that relation how do you get a measure of temperature. All these things are discussed. So there, one of the thing that was discussed is that these thermometers, where the substance that is used inside the thermometer is the gaseous substance, and then it can work both ways, like you can either keep the volume fixed and then your measurable quantity becomes pressure, like in this question, And or the other option is that you can keep the pressure fixed and then the measurable quantity becomes volume. So for gas, either of these two options can work. Then there are other things like for a solid metal, you have this resistance as the measurable quantity. Okay, and for a liquid, yeah, for metal you have the measurable quantity as the resistance, and then for a magnetic material your measurable quantity is magnetization or magnetic susceptibility, which has the temperature dependence, inverse temperature dependence. So anything that has a any thermometric property of that substance that has a temperature dependence, and measuring that property you can back calculate the temperature and thus get a measure of the temperature. So basically that's how the thermometer idea works. Thermometer is used to measure temperatures, right? So in this case you are using, in this question number 7, they are using a constant volume gas thermometer. So the element that is used inside the thermometer is a gaseous substance, and they have kept the volume as constant. So the pressure is the only varying quantity, or that is a quantity that will change with temperature and that you will measure. So the change in pressure will give you the idea of temperature. So it is said that there are two terms mentioned, ice point and steam point. So these are also mentioned in the lecture, but I'll also once again explain that ice point is basically mainly 0 degree centigrade point, and steam point is the 100 degree centigrade point. These are two fixed points which are ideally known for gases. That for ice point you have an equilibrium between ice and water. Okay, and that temperature is 0 degree centigrade. And for steam point, where you have equilibrium between the water and the vapor, uh, water I mean liquid state and vapor state, that is the steam point, which is 100 degree centigrade. So your ice point is basically the point of 0 degree centigrade, and steam point is known as the point to be 100 degree centigrade. Now when placed and at these 2 points, if let's say your 0 degree and 100 degree centigrade, you know those two values, right? So then you have the values mentioned of this pressure quantity, like let's say we call this 0 degree centigrade, the steam point ice point pressure as P naught. So P naught value is given as 80 centimeter of mercury height, that is 80 centimeter Hg. And let us call the steam point, that means 100 degree centigrade, corresponding pressure as P100, and that value is also given 109.3 centimeter Hg. And then when you have a known pressure of 100 centimeter Hg, then what is the temperature? So this is the thermometer idea. So the thermometric quantities, how do we calculate them? We have to use that concept. That let's say this question number 7. So thermometric properties are what? So these are the certain specific properties which has a dependence on temperature inside a material. Okay, let's say one such thermometric property is X for a material. Okay, so this X, let's say for the simplest possible case, X has a linear dependence on temperature. It is linearly proportional to temperature. That means X is proportional to theta. So X is such a thermometric property and theta is your temperature. Okay, that means if X is linearly proportional to theta, this is not chi, this is X. Okay, X is then, so I am just using the notation used in the lecture so that you can relate well. So X is then can be written as A theta plus B, where A and B are constants in this linear equation term. Okay, unknown constants, and you have to get this values of A and B from some other known values. How to get that? So there comes the idea of these two fixed points, ice point and steam point. So two fixed points, ice point and steam point, says 0 degree centigrade, theta naught, let's say, and theta 100 is 100 degree centigrade. These are 2 points where basically if you now put the now at 0 degree centigrade, this property, thermometric property, has a value of X naught, and at 100 degree the value is X100. So once you use this equation here and you put the value of theta as 0, because it is 0 degree centigrade, so here theta is in centigrade scale. Remember, here theta is equal to temperature, so do not confuse it and use it in Kelvin, because that will be wrong. So here theta is temperature in degree centigrade scale. Okay, so therefore you can directly put the value of theta as 0 in this case. So X equal to A into 0 plus b x naught, because at theta equal to 0 x equal to x naught, that means b equal to simply you get x naught, right? And the second case is that x 100 is at 100 degree centigrade value of x, that is a times 100 plus b. Now b value we already obtained as x naught, so this is 100a plus x naught. That means a is equal to just like x 100 minus x naught by 100. So thus, by using the known values of the thermometric property at two fixed point as steam point and ice point, you have solved the values of the unknown constants a and b. Now you can directly get x in the main equation. So x equal to a theta plus b, right? So a is now x 100 minus x naught by 100 into theta plus b is x naught. So you take this x naught to the other side. So x minus x naught equal to x 100 minus x naught by 100 into theta. So this is a like multiplication sign. Don't get confused. This is just multiplied theta. So then theta is the temperature in centigrade scale is just x theta. So this x we call as x theta now, because x value at temperature equal to theta degree centigrade is identified as x theta. Just like for 0 degree centigrade you call it x0, and for 100 degree you call it x100. Similarly for theta degree centigrade you call it x theta. X theta minus x0 divided by this x100 minus x0 into 100. So this is the expression of temperature. So this is how you calculate the thermometric properties. Here you can see that by change temperature variation of this thermometric property, which is x in this case, and by using the idea of two known fixed points, you can directly get the formula to calculate the when a certain degree centigrade theta is given, and the thermometric property at that temperature can be known as x theta when all the other parameters are known. So in our question they have asked us to calculate the temperature and not the quantity. So in this case, in question 7, the thermometric property that they have mentioned, x is equivalent to pressure, because they are measuring change of pressure of the constant volume gas substance in the thermometer. So x is nothing but the pressure here. So everything will be just the same. Just you have to replace the x by p. All other concepts will be same. So similarly, your theta will be then x is now p theta minus x naught is p naught divided by x 100 is p 100 minus again x naught is p naught into 100. So you have the already information about the all other quantities. Like they have mentioned that p naught equal to 80. Let us go back. What are the units? I have forgotten. So yeah, 7 is 80 centimeter Hg, 109 centimeter Hg, and this is 100 centimeter. So we have this is 80 centimeter Hg, P100 is 109.3 centimeter Hg, and P theta, which is at the unknown temperature theta degree centigrade, the value of pressure that is given is basically 100 centimeter Hg, because everything is in the same unit of pressure, centimeter Hg, so we will not convert it in a particular unit, so we will keep it as it is, because in the ratio the units will be cancelled out, right? So P theta is then 100 in centimeter Hg unit minus P naught is 80 divided by P100 is 109.3 minus 80. The centimeter Hg both top and bottom cancelled out into 100. So once you calculate this, you will get 68.26 degree centigrade. That is the temperature at which the pressure will be 100 centimeter Hg. So let us go back and check whether our calculation is right. So this option number D is correct, which is also the accepted answer. So this is done. Then question number 8 is about a constant volume hydrogen temperature is used to measure the temperature of a furnace. And the pressure in the bulb at 0 degree centigrade is equal to that of the atmosphere. If the temperature of the furnace is 270 degrees centigrade, what is the pressure in the bulb at the furnace temperature? Okay, so first of all, again you are using a thermometer which is a hydrogen thermometer. That means hydrogen gas is used, and similar to the question number 7, it is again a constant volume thermometer. That means the pressure of the gas is the only measurable quantity for you to get an estimate of the temperature. Now the pressure in the bulb at 0 degree centigrade is equal to that of the atmosphere. That means 1 atmospheric pressure is when the temperature is 0 degree centigrade, or you know now the value of the pressure corresponding to 0 degree centigrade, and it is mentioned that when the temperature is 273 degrees centigrade, then what will be the pressure value. So this question is a bit different from the earlier question in term, but this is also the formula needed here is also mentioned in the class, so you can follow that up for this question. So question number 8 is about, this is saying that at 0 degree centigrade the pressure P naught, let's say, is equal to 1 atmosphere, which is atmospheric pressure. Then at a different pressure, let's say this pressure we call it Pi. Okay, now at a different temperature T is equal to 270 degrees centigrade. So here 0 degree centigrade is 273 Kelvin, and 273 degrees centigrade is 273 plus 273 equal to 546 Kelvin. So at this temperature, if the pressure is P, then P is equal to what? So this is the only option, only known information you have is about 0 degree centigrade pressure, and the pressure temperature you need to calculate the pressure at. So here you have to use this formula that you know for gases, especially ideal gas, that is the approximation of real gas at in the low pressure limit. You know that the expression for a constant volume in ideal gas is P proportional to T, because for ideal gas PV is equal to RT. So at volume is equal to constant, you have your P proportional to T for ideal gas. That means pressure and temperature are directly proportional to each other. So if temperature increases, pressure will also increase, but this is only at low pressure P tends to 0 limit of real gases, right? So here you have this, because there is a directly proportional to relation, so you have T by Ti is equal to limit of P by Pi, where Pi is going to 0 limit at V is equal to constant, because there is a direct proportionality. So this is the formula that you are going to use here for calculating temperature. So instead of the two fixed point case like the earlier one, here you do not have the two information about the two fixed points, so you will not use that formula, but this formula will come as handy in this case. So in our case you need to calculate the pressure, right, P at temperature given. So P is equal to then Pi into T by Ti. Okay, so Pi is the pressure at 0 degree centigrade, which is 1 atmosphere, into T is the temperature at which you need to calculate, which is 546 Kelvin, divided by Ti is the temperature 0 degree centigrade, which is 273 Kelvin. So this is 2. So this is 2 atmosphere you are getting, that when the temperature is 273 degrees centigrade, the pressure of this case is 2 atmosphere. So this is our answer. Okay, so they have also mentioned, they have taken the unit in centimeter Hg, so that is no problem. Sorry, this is not the answer. So we have got 2 atmosphere, right, as the answer. We know that 1 atmosphere is the atmospheric pressure, which is nothing but 76 centimeter Hg equivalent of pressure. So 2 atmosphere will be simply like 76 into 2, which is just 152 centimeter Hg. Okay, so this is option number C will be the correct answer. So this, sorry, I by mistake I marked that, but 152 in centimeter Hg unit will be your answer, or in atmosphere unit it will be like 2 atmosphere. Now question number 9 is that in the interval of 0 degree to 660 degree centigrade, a platinum resistance thermometer is used for interpolating temperatures on international scale. If the variation of resistance with temperature is given by RT equal to R naught into 1 plus alpha T plus beta T square, then find the values of alpha and beta given R naught, R100 and R444.6. So basically again here there is a platinum resistance thermometer, that means platinum is a solid metal. So in this case the thermometer's measuring property will be the resistance of that metal, which is R in this case, and resistance has a temperature variation, and depending on that, depending on how it varies with temperature, we will measure the resistance and we can back calculate the temperature from there. So that is how this thermometer works. So the famous temperature relation of resistance that it follows from here is RT is equal to R naught into 1 plus alpha T plus beta T squared. Alpha and beta you have to calculate, and these values are given. So let us organize the equation here so that we can see how what we can do is that for the thermometer RT is equal to R naught into 1 plus alpha T plus beta T square, right? Now there are information, R naught value is given first of all, okay, and R 100 value is given, and R 444.6 value is given. So let me go again and check what was the value, or we can even yeah, so we need this question. I'll figure it out later what is the problem, but for now so the values are R 100 is 10 ohm, sorry, R naught is 10 ohm, R 100 is 13.946 ohm, 10 13.946 and 24.817. Okay, sorry, 13.946, I wrote it wrong. So 10 ohm, 13.946 and 24.817. Yeah, so this is 13.946. 24.817. So this is given. Now you just have to use this and put in the expression. So first of all, R 100 means your T is 100 here, right? So there you have this R 100 equal to 10 into 1 plus alpha 100 plus beta 100 squared equal to 13.946. Okay, so 1 plus 100 alpha plus 100 squared beta is equal to 1.3946. This is equation number 1. And R 444.6, where T is equal to 444.6 equal to R naught into 10 into 1 plus alpha into 444.6 plus beta 0.6 whole squared is equal to 24.817, which is like 1 plus 444.6 alpha plus 444.6 whole squared beta equal to 2.4817. This is equation number 2. Now using these two equations, you know you have two equation and two unknown parameters alpha and beta, so you know how to solve these kind of equations, right? Because basically using two unknown equations you have to solve for alpha and beta. So okay, so let us try to do this. So you can use any method suitable for you, because the idea is that you have two unknowns and two equations. So like for this case I can like alpha is equal to 1.3946 minus 1 minus 100 squared beta by alpha. So this is like 1.3946 minus 1. Okay, so this is 0.3946 minus this is 100 square, that means 100 into 100 into the power 4 beta by 100. So replacing this in 2, so in 2 you have 1 plus 444.6 into 0.3946 in minus 10 to the power 4 beta by 100 plus 444.6 squared into beta is equal to 2.4817. Now we can simplify this further so that you can get an equation in where the only unknown constant is beta. So this is 100, this 100 comes up, plus 444.6.3946 minus 10 to the power 4 beta plus 444.6 whole squared beta is equal to, oh sorry, this is another 100 that will be multiplied here, because this 100 comes here in this term and this 100 also contributes here in this term. So this into beta is equal to 2.4817 into 100. Okay, because this whole thing is by 100, so this is into 100 on the other side also. So what are the terms dependent on beta? Then separate that first. So 444.6 into 10 to the power of 444.6 into 10 to the power of 4 is equal to, this is in minus this term, then plus 444.6 whole squared into 10 squared beta, this is plus, and the rest of the terms, this is 100 multiplied, that means 248.17 minus this 100 comes here on the other side and minus this thing, this product 444.6 into 0.3946, right? So this is equal to beta into 444.6 into 10 square, you can take also common. So this is 444.6 into 10 square taken common, so this minus 1 into 10 squared is equal to this whole thing, that 248.17 minus 100 minus 444.6 into 0.3946. So this is we are getting as minus 27.269, let's say, and here you get beta is equal to then minus 27.269 divided by 444.6 minus 100, this 10 square is 100, so divided by this thing becomes 344.6 into this 444.6 into 10 squared. So this is like 27.269 divided by 344.6 into 444.6 into 10 squared. So the whole thing gives you beta is equal to minus 1.78 into 10 to the power of minus 6. And beta is basically what will be the unit, because this is r equal to r naught into 1, this is beta into t squared is equal to the, so this will be like, I think, degree centigrade divided 1 by degree centigrade square, so degree centigrade to the power minus 2. Okay, so let us check whether this value is correct, because the calculation might be where I have made some small mistakes. So maybe first take that and then we proceed on calculating the other value. So what is the closest that we have got? So I think we have got 1 point, so minus 6 order is right. Then we have got yeah 1.78. Okay, so there can be some order, like the order came right. So let us go and check alpha, then again check the options. So even if there is some problem in the calculation, I think that can be solved, because eventually you just need to solve a two unknown constant equations, right? So alpha is 0.3946 minus 10 to the power 4 beta by 100. So 0.3946 into 10 minus 10 to the power 4 beta by 100, which is like 0.3946 minus 10 to the power 4 into beta, because basically this is also minus, so minus and minus makes it plus 1.78. Okay, into 10 to the power minus 6 into 10 to the power 4 is 10 to the power minus 2. 1.78 into 10 to the power minus 2 divided by 100. So this is what you are getting, is that 0.3946 plus 1.78 into 10 to the power of minus 2 divided by 100. So you are getting 4.12 into 10 to the power of minus 3. And here it will be part degree centigrade or degree centigrade to the power minus 1, because here it is alpha times T only, right? So let us go back and check. Okay, so the answers that we have got are not exactly same, like not exactly same as the given option, but at least we can check what is the closest one, because the answer can be a little bit different depending on how much decimal places you have approximated the answer to. But mostly our answer is like matching with this one, because the alpha value was 4 point something 10 to the power minus 3 per degree centigrade, and beta value was some minus 1.7, but here they are 1.65, but that's okay because that is close, right? But this, in this case, like in alpha value is 4 point this thing, but beta value is completely off, so this is not the exact value. And also for this case where alpha beta value is 1.78 something like that, closer to ours, but here this is 3.56. So I think this is the correct accepted answer is also A. So even if there is a slight mismatch in the beta value, I think that can be sorted out by taking the decimal places into consideration, but this is the correct calculation that we have done. Okay, so for the final question, it is mentioned that the resistance of a platinum resistance thermometer at 0 degree centigrade, 100 degree centigrade and 200 degree centigrade is found to be 3.5 ohm, 5.5 ohm and 7.44 ohm respectively. Then calculate the value of delta for platinum. So this is also the formula that you need to use here, is mentioned at the very last part of this week's lecture. So we'll solve this. Question number 10 is that for platinum thermometer as resistance thermometer that you are using, and the value at 0 is given 3.5 ohm, and 100 is given 100 degree centigrade 5.5 ohm, and 200 degree centigrade is also given, that is your is, I think, theta, right? Okay, so 200 was 7.44 ohm. Then delta is basically as per the standard formula, so I will not derive the formula again here because that is already done in the lecture. But delta is basically a correction term sort of that you have from the temperature scale and actually this degree centigrade temperature, right? So that delta has a direct formula related to temperature and we will directly use that. But R 200 is basically 7.44 ohm. So this is now you know from the discussion of like thermometric properties that if your theta is the temperature and R is a measurable quantity, then theta will be like R theta minus R naught by R100. So you just replace the X by R here, because here the measurable quantity is R. So resistance. So this is into 100. This is theta P. What is theta P? Theta P is some temperature scale that is not in Celsius scale, but a temperature scale not in Celsius scale, whereas theta is the actual Celsius scale temperature. Okay, so now you have to calculate what is the correction, what is the difference between the actual Celsius scale and what is the and between the temperature that we are obtaining from the thermometric properties, that is not in actual Celsius scale. So the difference in theta and theta P is the correction term delta that you need to calculate from here, and that has a direct formula, such as how do you get that formula is basically I'll first write down the formula, and then maybe we can calculate what is the value. Okay, so yeah, so what is what will be, yeah, so let me calculate the value first. That the formula that is straightforward, that is also mentioned in the lecture. Sorry, this is not delta, that is why I was confused about. This is not delta. So this theta and theta minus theta P is the difference between the actual Celsius temperature and the temperature you're getting for thermometric property measurement. So delta has a relation to that theta minus theta P, that theta minus theta P is equal to, supposed to be delta into theta by 100 whole squared plus minus theta minus theta by 100. So once you have that, so basically you have yeah, so you have to substitute the value of theta P that we had written down just before. So this is theta minus R theta minus R naught divided by R100 minus R naught into 100. So this is theta minus theta P that we are writing now. So this is the formula, that the final formula that we'll be needing. So if this is theta minus theta P, then we further simplify it. This is theta minus R theta is nothing but R naught into 1 plus alpha theta plus beta theta squared, right, minus R naught divided by R100 is again R naught into 1 plus alpha times 100 plus 100 squared beta minus R naught into 100. And now you take R naught common from numerator and denominator. So this R naught and R naught cancels out top and bottom. So this is 1 plus alpha theta plus beta theta squared minus 1 divided by 1 plus 100 alpha plus 100 squared alpha beta minus 1. So this 1 and 1 cancelling out. This is also cancelling out into 100. So what you are getting is theta minus alpha theta plus beta theta squared into 100 divided by 100 alpha plus 100 squared beta. Further simplify it, you will get 100 alpha theta plus 10 to the power 4 beta theta minus 10 squared alpha theta plus 10 squared beta theta squared. This is also minus. So this thing and this thing is same. So this cancelling out, divided by 100 into alpha plus 10 squared beta. So you are left with 10 to the power 4 beta theta minus 10 square beta theta squared, right? So you have you can further simplify that. You can take it as common. Alpha plus 100 beta and from the top you have square, so 100 is getting common from here, so 100 beta theta minus beta theta squared, this is equal to 10 alpha plus 100 beta this beta is taken as common, theta by 100. Okay, so if you are taking 100 in the denominator, so you have to take a 10 to the power 4 here to adjust that, minus theta squared divided by, to take 10 to the power 4 common, you have to also divide it by 10 to the power 4. So ultimately you are getting theta minus theta p is equal to, take minus sign as common, so this is 100 squared beta divided by alpha plus 100 beta into, this thing comes first, then 100 theta by 10 squared, or sorry 100 theta by 100 whole square, because this is 10 to the power 4, sorry this is 10 to the power 4, so this is theta by 100 whole square minus theta by 100. Okay, so this is the whole thing, and this term, you know that this is formally given the sign of delta. So delta, if you want to calculate, delta is minus 100 squared beta divided by alpha plus 100 beta. Okay, so right, so now in the question you are given the values of all the three resistances. So just like in question number 9 where you had the resistance values and you had calculated the alpha and beta values, right? So similarly you have to do here as well, then get those alpha and beta value, put that here and get the delta value. So I'll just write down the equations for you, then you can maybe solve the equation like the alpha and beta by yourself, and I'll let you know the final answer. So basically it was given that 0 R naught is 3.5, then 100 is 5.5, 200 is 7.44. So R naught is 3.5 ohm, that means a 0 degree centigrade. So our 100 is equal to R naught into 1 plus alpha t plus beta t squared is equal to 3.5 into 1 plus alpha into 100 plus 100 squared into beta is equal to your 100 Kelvin resistance is 5.5. So this is your equation number 1. Okay, and as equation number 2 is R200 is equal to R naught 3.5 into 1 plus 200 into alpha plus 200 squared into beta is equal to, the resistance is 7.44. So this is equation number 2, right? So by solving equation 1 and 2, you will solve the values of alpha and beta. Okay, just like we did for question number 9. Similarly do this, and once you get alpha and beta, you just put those values in delta. So this is minus 100 squared beta by alpha plus 100 beta. So once you put those and solve alpha beta and put it here, so alpha final delta value, you can check that you will get 1.5, I think. So just let us check the right answer whether that is accepted or not. Yes, so accepted answer is B. So here you can see that your option number B is 1.5. So just the calculation part I have skipped because that is just the same calculation. But once you get alpha and beta, you can get the value of delta for platinum, which is 1.5 in this case. So this is all for this week's tutorial, and if you have some questions or doubts, you can let me know, or you can even discuss it in the discussion forum, or else we'll meet in the next lecture.